The universe is a tapestry of mysteries, woven with threads of light, time, and the invisible forces that hold it all together. Imagine for a moment standing at the edge of reality itself, peering into a void where time slows to a crawl, where the laws of physics as we know them twist and unravel. What if a group of scientists, tucked away in a lab on American soil, accidentally tore a tiny hole in that tapestry, a fleeting, stable rift in the fabric of the universe? The rumors swirling around Fermilab, a beacon of cutting-edge physics, suggest something like this might have happened. Not a gaping portal to another dimension, but something subtler, stranger, and far more real than the wildest science fiction. The story begins with a whisper, a flicker of data that didn't make sense, and a simulation so precise it blurred the line between theory and reality. It's a tale that pulls you in with the weight of curiosity, the thrill of the unknown, and the quiet dread of what might happen if we push the boundaries of existence just a little too far. In late 2022, deep within the sprawling campus of Fermilab in Illinois, a team of scientists led by physicist Joe Licken did something extraordinary. They didn't fire up a particle collider to smash atoms or hunt for elusive particles. Instead, they turned to a quantum computer, Google's Sycamore processor, a machine so advanced it feels like it belongs in a future we haven't yet reached. Their goal was to simulate a wormhole, a theoretical tunnel through space-time that could connect distant corners of the universe or even different realities. Picture it, a bridge where information, energy, or even matter could slip from one point to another, defying the rules of distance and time. This wasn't about physically ripping open the cosmos, no swirling vortex or cosmic catastrophe. It was a digital experiment, a mathematical dance of quantum bits, or qubits, choreographed to mimic the behavior of a traversable wormhole. But what they found sent ripples through the physics world, not because they created a real hole, but because the simulation was too real. The quantum information they sent through their virtual wormhole behaved exactly as Einstein's equations predicted it would in a real space-time tunnel. It didn't collapse. It didn't fizzle out. It held stable, coherent, measurable, for just long enough to make everyone in the room pause. To understand why this matters, let's step back and think about what a wormhole represents. It's not just a sci-fi trope or a plot device for interstellar travel. In Einstein's theory of relativity, a wormhole is a place where space-time folds in on itself, a shortcut where the rules of reality bend. Time, as we experience it, might slow or even stop at its heart. It's a glimpse into the end of time itself, a place where the universe's clock ticks differently. The Fermilab team didn't create a physical wormhole, but their simulation was so precise that it mirrored the mathematical behavior of one. They encoded quantum information at one point in their system and watched it emerge at another, as if it had traveled through a tunnel of space-time. This wasn't a cartoonish portal glowing with cosmic light. It was a quiet, invisible triumph of code and physics. The qubits followed the exact equations that govern theoretical wormholes, moving through a digital realm that felt eerily like the real thing. Joe Licken himself called it a profound bridge between quantum physics and gravity, two realms of science that have stubbornly refused to align for decades. It was as if they'd built a tiny, perfect model of the universe's deepest secrets and watched it hum with life. But then the whispers started. On physics forums, in hushed conversations at conferences and across social media, rumors began to spread that something more had happened at Fermilab. Not in the pristine, controlled environment of a quantum computer, but in the real world, where particle accelerators hum and sensors blink with data. The story went that in 2021, during a routine test involving legacy equipment from the Tevatron, Fermilab's now retired particle accelerator, something strange occurred. Unverified accounts from people claiming to be near the facility described anomalous spikes in sensor readings, fleeting moments where the data didn't add up. These weren't the usual blips of particle collisions or equipment hiccups. They were gaps, moments where measurement seemed to vanish, as if a piece of reality had blinked out of existence. Some called it a stable hole, a pocket of space-time that didn't behave like the rest of the universe. Others speculated it was a cue ball, a theoretical lump of energy so dense it could warp the fabric of reality itself. These stories were unconfirmed, dismissed by official channels, but they clung to the edges of the scientific world like shadows, fueled by the tantalizing possibility that Fermilab had stumbled onto something they weren't ready to understand. What makes these rumors so gripping isn't just the idea of a hole in the universe. It's the question of what such a thing would mean. A cue ball, first theorized by Nobel laureate Sidney Coleman in the 1980s, isn't a black hole or a wormhole, but something stranger. It's a stable knot of energy, a bubble where the universe's baseline rules shift. Imagine a spot where the laws of physics feel different, where particles move as if they're in a slightly altered reality. In certain theories, these cue balls could form when the Higgs field, the invisible force that gives particles mass, condenses into a coherent, spherical structure. To a sensor, it might look like a void, a place where normal spacetime doesn't apply. The rumors suggested that Fermilab's experiments, with their precise control over quantum fields, might have accidentally created such a structure if only for a fraction of a second. No one claimed the world was at risk, but the idea that we could brush up against something so alien, so fundamentally other, sent a shiver through those who heard the tale. It was as if the universe itself had whispered, "You're closer than you think." The whispers about Fermilab's supposed stable hole didn't just fade into the background noise of the internet. They grew, twisting through online forums and late-night discussions like a ghost story told around a campfire. What made these rumors so hard to shake wasn't just the allure of a cosmic mystery, but the way they danced on the edge of possibility. The universe, after all, isn't as stable as it seems. Beneath the surface of everything we see, the stars, the galaxies, the quiet hum of our everyday lives, lies a reality that's fragile, teetering on the edge of something deeper, something unknown. Scientists have long suspected that our universe might exist in a false vacuum, a state like water cooled below freezing but not yet turned to ice. One wrong move, one tiny push, and it could crystallize into something entirely different, with new rules, new physics, a new everything. The idea that Fermilab, with its particle accelerators and quantum computers, might have brushed against this edge was enough to make even the skeptics pause. What if, in their quest to understand the universe, they'd accidentally nudged it toward a truth it wasn't ready to reveal? Let's dive deeper into the science that fuels these rumors, not with cold equations, but with the sense of awe they inspire. The Fermilab team's quantum simulation wasn't just a clever trick. It was a window into a realm where the boundaries of reality blur. Their work with Google's Sycamore processor showed that quantum systems could mimic the behavior of a wormhole, a tunnel through space-time that could, in theory, connect two distant points or even two universes. But the real magic happened in the stability of their creation. Most simulations flicker and collapse, unable to hold the delicate balance of quantum information. This one didn't. For a fleeting moment, the qubits danced in perfect harmony, mimicking the flow of energy through a real wormhole. It was as if they'd captured a piece of the cosmos in a digital cage, watching it pulse with life before it vanished. This wasn't just about wormholes, though. It was about what they represent. A crack in our understanding of reality, a hint that the universe might allow shortcuts, detours, or even escape routes to places we can't yet imagine. But the rumors weren't about the simulation alone. They pointed to something physical, something that might have happened in the real world. The stories centered on the Tevatron, Fermilab's legendary particle accelerator, which had been shut down in 2011 but still hummed with activity for smaller experiments. In 2021, during one of these legacy tests, something odd reportedly happened. Sensors, designed to catch every fleeting particle, registered anomalies, spikes, and gaps that didn't match any known pattern. Imagine a scientist staring at a screen, expecting the usual cascade of data, only to see a moment where the numbers just stopped. No explanation, no glitch they could pinpoint. Some whispered it was a cue ball, that strange knot of energy theorized by Sidney Coleman, a bubble where the Higgs field twisted into something new. Others speculated it was a topological defect, a cosmic scar left when the universe's rules shifted for a split second. These ideas weren't born in a vacuum. They came from decades of theoretical work suggesting that our universe might not be the final word, that it could harbor pockets of alternate reality, fleeting and fragile, but real enough to leave a mark. What makes this so gripping is the human element. The scientists at Fermilab, people like you and me, wrestling with questions that feel bigger than any one mind can hold. Imagine being Joe Licken, standing in a lab surrounded by blinking monitors, knowing your team has just simulated something that could rewrite the rules of physics. Or picture a technician, late at night, noticing a flicker in the data that doesn't belong, a moment where the universe seems to hold its breath. These aren't just experiments. They're acts of courage, of daring to touch the unknown. The rumors, unverified as they were, spoke to a deeper truth. We're no longer just observing the universe. We're poking at it, prodding its edges, asking what happens if we push too far. The idea of a stable hole isn't just about a glitch in space-time. It's about our own audacity, our willingness to chase answers even when they scare us. And what scares us most is the possibility that the universe might answer back. Then there's the question of what a stable hole would even look like. Not a swirling vortex or a glowing portal, but something subtler. A region where light bends differently, where time feels wrong, where the rules of cause and effect fray at the edges. Theoretical papers tucked away in academic journals describe phenomena like causal disconnection, where a tiny pocket of space-time becomes untethered from the rest of the universe. Information can't flow in or out, as if that spot has slipped into a different reality. To a sensor, it might look like a blank spot, a place where data vanishes. To a person standing nearby, it might feel like nothing at all. Or it might carry the faint, unshakable sense that something isn't right. The rumors about Fermilab suggested that such a phenomenon, if it happened, would have been fleeting, lasting less than a trillionth of a second. But even a moment like that could change everything. It would be proof that our universe isn't as solid as we think, that we're living on a thin membrane stretched over something vast and strange. The idea of a stable hole in the universe lingers like a half-remembered dream, both thrilling and unsettling. It's easy to get lost in the what-ifs. What if Fermilab really did brush against the edge of reality? What if, for a fleeting moment, they created something that wasn't supposed to exist? But as the rumors swirled, a quieter truth emerged, one grounded not in cosmic catastrophe, but in the relentless curiosity of those who dare to ask the biggest questions. The universe, it turns out, has its own safeguards, its own way of keeping the fabric of reality intact. And yet, the work at Fermilab, both the quantum simulations and the whispers of anomalies, points to a future where we might not just observe the cosmos, but reshape our understanding of it. This is a story of boundaries pushed, of mysteries glimpsed, and of a universe that holds its secrets close, revealing them only to those who are brave enough to look. Let's pull back the curtain on what really happened, or didn't, at Fermilab. Despite the tantalizing rumors, there's no evidence, no peer-reviewed paper, no official record that suggests a physical hole in space-time was ever created. The whispers of anomalous sensor readings and data blackouts during a 2021 Tevatron test remain just that. Whispers, unverified and unsubstantiated. Fermilab's scientists, including Joe Licken, have been clear. Their groundbreaking wormhole simulation was just that, a simulation. It ran on Google's Sycamore quantum processor, a marvel of modern technology, but it was a digital construct, not a physical rift. The Guardian, covering the experiment, emphasized that no actual rupture in space-time occurred. The quantum information that danced through their virtual wormhole followed the rules of theoretical physics with eerie precision, but it was all contained within the safe, controlled environment of a computer. The rumors of a stable hole seem to have grown from a mix of misunderstanding, speculation, and the human tendency to see mystery in the unknown. But the absence of a real hole doesn't diminish the wonder of what was achieved. It only sharpens the focus on what's possible. What makes this story so compelling isn't the lack of a cosmic disaster, but the way it reveals the delicate balance of our universe. Scientists like Sidney Coleman and Frank DeLucia, in their groundbreaking 1980 work on vacuum decay, showed that even if a tiny bubble of true vacuum were to form, a region with different physical laws, it wouldn't spell doom. The universe has a kind of cosmic immune system. Gravitational forces would crush such a bubble before it could grow, collapsing it in a fraction of a second. This isn't just a mathematical curiosity, it's a profound reassurance. Even if Fermilab's experiments had accidentally nudged the Higgs field into a strange new configuration, the energies involved are far too small to create anything lasting. Cosmic rays, slamming into Earth's atmosphere with millions of times more energy than any particle accelerator, have been testing these limits for billions of years. If a stable hole or a vacuum bubble could destroy the universe, it would have happened long before we started building machines to probe the cosmos. The fact that we're here, telling this story, is proof that the universe knows how to protect itself. Yet the work at Fermilab isn't slowing down. It's evolving. As particle accelerators like the Tevatron reach their limits, quantum simulation is opening new doors. The wormhole experiment was just the beginning, a proof of concept that we can model the universe's deepest secrets without risking reality itself. Imagine a future where quantum computers don't just simulate wormholes but explore the birth of black holes, the collapse of stars, or the fleeting moments of the Big Bang. These simulations aren't just academic exercises. They're windows into questions we can't answer with telescopes or colliders. Why does gravity resist unification with quantum mechanics? What happens at the edge of a black hole's horizon? Could there be other universes just beyond our reach, with their own rules and realities? Fermilab's shift toward quantum simulation reflects a broader truth. We're entering an era where the line between theory and experiment blurs, where we can test the impossible without leaving the lab. It's a tightrope walk, balancing the thrill of discovery with the safety of the world we know. This brings us to the heart of what Fermilab is doing today, far from the sensational headlines. The Deep Underground Neutrino Experiment, or DUNE, is sending ghostly particles across 800 miles of Earth, chasing clues to why matter exists at all. The Muon G2 experiment is probing tiny anomalies in particle behavior, hinting at forces or particles we haven't yet discovered. Dark matter detectors are searching for the invisible stuff that makes up most of the universe's mass. These projects don't need cosmic holes to be revolutionary. They're rewriting our understanding of reality one quiet discovery at a time. And yet, the rumors of a stable hole remind us of something vital. Science isn't just about answers. It's about the questions that keep us awake at night, the ones that make us wonder if we're on the verge of something bigger. If Fermilab ever does create a real hole in the universe, it won't be an accident. It'll be because they've unlocked the code to the cosmos itself. So where does this leave us? Standing at the edge of the unknown, peering into a universe that's both more fragile and more resilient than we ever imagined. The story of Fermilab's stable hole isn't about a disaster that never happened. It's about the human drive to push beyond what's safe, what's known, what's possible. It's about the courage to build machines that mimic the stars, to write code that echoes the birth of time, to chase truths that might change everything. The universe didn't unravel, but the questions raised by Fermilab's work will ripple forward, inspiring new experiments, new ideas, and new ways of seeing the world. Maybe one day we'll look back and realize that this was the moment we began to understand not just our universe, but the infinite possibilities beyond it. Until then, we keep asking, keep searching, and keep listening for the universe's next whisper.